Hello everybody. I am very pleased to share my work D3G, exploring Gaussian prior for temporal sentence grounding with glance annotation. Temporal sentence grounding, TSG, aims to locate a specific moment from an untrimmed video with a given natural language query. Recently, weakly supervised methods still have a large performance gap compared to fully supervised ones, while the latter requires laborious timestamp annotations. In this study, we aim to reduce the annotation cost yet keep competitive performance for TSG task compared to fully supervised ones. To achieve this goal, we investigate a recently proposed glance-supervised temporal sentence grounding task. Glance-supervised temporal sentence grounding is firstly proposed in paper Vega. Vega first cuts the input video into clips of fixed length, which are assigned with Gaussian weights generated according to the glance annotation, and contrasts clips with queries. However, there are few obvious drawbacks. First, clips of fixed length cannot cover a wide range of target moments, which inevitably aligns the sentence with incomplete moment and obtains suboptimal performance. Second, the fixed Gaussian prior tends to be affected by glance annotation bias, since the glance annotations are not guaranteed at the center of target moments. Besides, some complex moments consist of multi-events cannot be well described by single Gaussian distribution. To address the aforementioned defects and fully unleash the potential of Gaussian prior knowledge with the low-cost glance annotation, we propose a dynamic Gaussian prior-based grounding framework with glance annotation, D3G. Specifically, we propose a semantic alignment group contrastive learning module to align the features of the positive sentence moment pairs and a dynamic Gaussian prior adjustment module to ease the annotation bias and model the distributions of complex moments. Extensive experiments demonstrate that D3G obtains consistent and significant gains compared to method under the same annotating paradigm. This the overview of proposed D3G. Given the video and query, we basically following MMN extract the features of sentence and video clips, respectively. We then introduce our adapted SAGCL module and DGA module to fully exploit the prior information from glance annotation. In the SAGCL module, we aims to mine reliable positive moments and align the positive sentence moment pairs in the joint embedding space. Given the encoded video's features F, we first generate abundant candidate moments following 2D, tan. We then compute the Gaussian prior for each moment as shown in equation 3. Since the glance is not very reliable, we further compute the relevance between query and each candidate moment to rectify the prior of candidate moments. Finally, we contrast the given query sentence with a group of positive sentences. Note that different positive moments are assigned with corresponding prior weight. In this way, SAGCL effectively avoids being dominated by inaccurate moments with less similarity and tends to mine the candidate moments having large overlap with the target moment. Although rectified Gaussian prior can alleviate the annotation bias to some extent, it's still hard to well describe complex moments with single Gaussian distribution. To further ease the annotation bias and characterize complex target moments, we propose a novel dynamic Gaussian prior adjustment module, DGA. In DGA module, we continuously update the relevance between glance frame and other frames and mine latent local centers of target moments. We then jointly fuse multiple Gaussian distributions to obtain more reliable prior. In order to validate the effectiveness of the proposed D3G, we conduct extensive experiments on 3 publicly available datasets, charades, tacos and ActivityNet captions and report metric following previous works. As shown in Table 1 and Table 3, compared to Vega, D3G achieve consistent improvements with same video features. Specifically, D3G significantly exceeds most of weakly supervised methods by a large margin with trivial increment of annotation cost. Since PSVTG and PFU adopt more robust I3D feature, they obviously outperform D3G on charades STA. However, D3G instead is superior to PSVTG on more challenging tacos with same features. As for ablation study, we first the effectiveness of different components of the proposed D3G. As shown in Table 4, the SAGCL brings notable performance gains compared to simplified SAGCL module. After equipped with DGA module, the accuracy is improved largely at higher IOU. In Table 5, we also verify that both Gaussian prior and semantic consistency are crucial to sample positive moments. As for top case sampling strategy, we observe that sampling enough latent positive moments is beneficial to mining target moment for training. As for tolerance to extreme glance annotation, the performances of D3G are relatively stable compared to Vega as shown in Table 6. To clearly reveal the effectiveness of our method, we visualize some qualitative examples from the test split of charades STA dataset and ActivityNet captions dataset. Compared to Vega, D3G well align the query with the corresponding both simple and complex moments. That is all, thanks for your listening. Please feel free to contact me if you have any questions.